Good morning, all. Today we will discuss about some of the topics which are related to the blast furnace. So the first one is the refractories used in the blast furnace. As we all know that blast furnace from the outside it's a steel structure, but inside it is lined with the refractory. In fact, all high temperature uh, furnaces or transfer ladles, converters, all these are from the outside it looks like a steel vessel, but inside it is a refractory lined system. So here also, as far as the blast furnace is concerned, we have refractories at different parts of the blast furnace. As we discussed in the previous class, that there are various parts of the blast furnace. Starting from the top, you have mouth, and then you have a stack, then you have a belly, then you have a wash, then you have hearth. So at every part of the blast furnace, we use different kinds of uh, composition, proportion of refractory bricks. Depends upon the kind of the environment at that position it is prevailing. So based upon that, the kind of refractories will be used. So you can see that in the upper stack part of blast furnace, the kind of environment or the kind of situation, if you see, this location will prone to impact as well as abrasion caused by the raw materials during its charging process. So these refractories, whatever we are using at this particular location, should have resistance to this attack. Similarly, the middle stack, here also again, the kind of environment you have, this the alkali attack may takes place, alkali vapors that may come in contact with the refractory walls at this particular area, and certainly penetration of these vapors into the refractory lining will lead to formation of low melting compounds, and in course of time it may undergo failure also. So apart from that, again, the middle stack also to a certain extent will undergo abrasion because of the movement of the burden, because it is a continuous uh, process. The burden continuously moves from top to the bottom, and also there is a possibility of CO attack also may take place, because at these regions there is a possibility that solution loss reactions may take place, and that leads to formation of CO, and the CO attack also may possible at this particular location. So the refractories, whatever we're using at the middle stack, should have a resistance to this kind of conditions. Similarly, the lower stack, or you can say the beginning of the belly part of the blast furnace. So here also there is a possibility of CO attack and alkali attack may takes place. Along with that, a certain high temperature may also get prevail at this particular temperatures. Similarly, the wash part of the blast furnace, here also there is a possibility of alkali attack may take place, and especially the slag attack. It means the wash slag, which is initial slag is formed in the blast furnace. So that um, when it comes in contact with the refractories, there is a possibility of slag attack may take place. So your refractories should have resistance to this slag attack. Similarly, you have um, the hearth part of the blast furnace, where the entire burden will be going to liquid form. So the hearth is the region where it is a sink for the liquid products, slag as well as the hot metal. Okay. So there also there is a possibility that hot metal and slag uh, may come continuously in contact with the refractory lining. So the refractories should have resistance to the penetration of these liquid products. Similarly, the cap hole also it's a refractory lined system, and it should have resistance to erosion. Okay. Because during the tapping of hot metal, so it comes out with very high velocities. So because of which there is a possibility that erosion of the tap hole may take place. So it should have a resistance to the erosion. So these are the um, some of the problems or prevailing inside the blast furnace, and the kind of the refractory bricks what we are selecting to make sure that as per the condition which is prevailing inside the blast furnace, the environment which is prevailing inside the blast furnace, accordingly we need to use the different proportion of composition of the refractory bricks such that they can sustain those environments, and refractory life will be enhanced. So you see, as we discussed, that at the stack part of the blast furnace, most of the time there is a possibility that there is an abrasion may takes place, and SIBO attack may take place. So we have to make sure that refractories should have a property such as it should have good abrasion resistance as well as um, low permeability, so that these CO gases or the alkali vapors cannot penetrate into the refractory bricks. So here we are basically using the stack part, especially we are using high duty fire bricks. Okay, this is having Al2O3 ranging from 35 to 40%. 35 to 40% of Al2O3 fire bricks are used at the stack part of the blast furnace. And especially at the lower stack part, you see there we are using these fire bricks of having Al2O3 content approximately 60%. So in the wash part of the blast furnace, as we discussed just now, that this is the area which should withstand the high temperatures as well as the erosion by the hot blast which is generating in front of the piers, and then the lime and alkali slag attack. Okay, so this is the region. This is the condition which is prevailing in the in the wash part of the blast furnace. So to overcome or to sustain this kind of environment, the linings requires high refractiveness and refractoriness under load. So Bosch lining should be of the aluminum fire bricks with having a Al2O3 45 to 65%. Okay. So as we all know that as Al2O3 content is keep on increasing, the refractoriness will be increased. Okay. So at high temperatures, make sure that a more Al2O3 refractory bricks are to be used to sustain those high temperatures. And the hearth part of the blast furnace, if you see, so that is the region where you have high temperatures, and there is a possibility that corrosion of the refractory bricks may also takes place because of hot metal, continuous contact of hot metal as well as the slag. Okay. And also breakouts of the factories is a serious problem in the hearth part of the blast furnace. And so this to overcome this, so we have to use the refractory bricks which should have a low permeability and very low porosity. Okay. So here we are using the hearth part. We are using carbon blocks because carbon is not wetted by metal or slag, and certainly it is a chemically inert. Um, so that's why we are using carbon blocks in the hearth part of the blast furnace. So raw material what we use for the manufacturing of the carbon blocks is nothing but it's just a mixture of tar and pitch. These are with the byproducts of the oven process. And to enhance the life of the refractory bricks inside the blast furnace, and also to overcome the thermal shocks and all, we usually have a water cooling jacket system will be there in the toward the um, height of the blast furnace. So that it maintains the temperatures within the furnace, and also it also prevents the expansion of the factory bricks. So these are the water cooled jackets. You can see how these are arranged. These are the refractory bricks, and behind this there is a water jacket system is there, and behind this you will be having a the steel shell. Okay, so you can see the whatever the this water jacket you are seeing, this actually looks like this front part, and the back part is something like this. And from one side the water enters into the um, this cooling pad, and from the other side this comes out. So it is continuous water circulating system. Okay, which helps in um, avoiding thermal expansions and all of the refractory bricks inside the blast furnace. Then pure assembly, the hot blast, whatever are generated in the blast furnace stoves. So these hot blasts are sent to the hot blast main from the stoves, and it is connect. This hot blast main is connected to the bustle pipe, and to this bustle pipe, the clear stocks are fixed. Okay, so you can see in the clockwise direction, you can relate the things. That this hot blast main actually comes from the blast furnace house, where the preheated air is allowed to pass through this hot blast main, and this hot blast main is connected to the bustle pipe, and to this bustle pipe is actually connected around the periphery of the blast furnace, and to this bustle pipe, a series of tuyer stalks are connected, and this is how the basically in the tuyer stalk looks like. So you can see you have there's a tuyer stalk, and you have at this location you have gooseneck, where you can actually keep into the rear part of the blast furnace, where through that you can see how the PCI injections are going on into the blast furnace. Then you have then you have a blowpipe. This is a blowpipe, and this is called actually the pier, which is projected into the blast furnace. So something like this. Okay. So like this, a series of piers are arranged along the periphery of the blast furnace. Yeah, so you can see the same thing. This is actually the peephole, where you can see the same thing here. This and this both are same, where there is a glass will be there. From here you can see how the PCA injections are actually going on. So this is the tuyer stalk, and to this tuyer stalk you can see this is nothing but the pipe through which the PCI is actually injected, which is actually inserted from the side into the tuyer stalk. The small this same pipe is actually kept here for your understanding. So this is the pipe which is actually inserted here into the tuyer stalk, and through this your PCI injections will be actually taking place. Okay. Now we will discuss about blowing in process of blast furnace. Like if you are uh, commissioning a newly lined blast furnace, then or if the blast furnace is shut down for any reason, and you are again restart those shut down blast furnace, then we need to follow some sequence of operations, standard operating procedures. Um, this is this is this procedure is followed in two cases. One is when the furnace is shut down and again you are restarting it, or when you are commissioning a newly lined blast furnace. In these two cases, we basically follow the blowing in process. There is nothing but the blowing in process, starting off the newly lined blast furnace, nothing but the blowing in process. And this consists of a sequence of the operations. That is, one is the first step is called as a drying stage, and then the second stage is filling, and the third one is the lightning, and fourth one is the operating until routine practice is achieved. So these are the four stage process for starting off a newly lined or a shutdown blast furnace. So first step is a drying process. So the newly lining of the furnace basically contains a significant of moisture will be there. So this moisture should be removed um, before you generate the actual temperatures within the furnace. And for this drying process, we follow different methods. One is use of hot blast air. So the hot blast temperature is maintained at around 200 to 220 degrees centigrade, and that can be slowly increased to around 400 degrees centigrade. And this hot blast is basically inserted inside the blast furnace through the piers. And also this can be also inserted um, hearth in the hearth part of the blast furnace also. Okay, so the pipes are basically installed inside the piers of the blast furnace to direct heated air down to the blast furnace hearth. And this drying operation, see, there are certain holes through which you can actually inject or insert anything. One is your tap hole, other one is you have piers. So these are the you can say the inlet for anything to insert into the blast furnace during the blowing in process. Okay. So through these holes, the hot blast air is basically purged into the blast furnace, so that the entire blast furnace will be um, dried completely. And this drying process basically takes place at least 1 week. This is one method, that is utilization of hot blast air. Second one is hearth fire method. So this is basically consisting of filling of the hearth with wood or coke fire. So if you just fill it and then you just ignite it so that it keeps on heating and the drying will take place. These are the two. So once the drying is done, then second one, as I said, this next one is the filling. So once the drying is done, then you need to fill the blast furnace to certain height, some of the fuels. Okay. So second step is the filling. Filling the hearth with light firewood saturated with oil up to the clear level. And then coke is charged from top up to the Bosch level. Means you should now to generate the actual blast furnace temperatures within the furnace. We should first fill the furnace from the from the bottom, from the hearth part to the pier level with firewood filled with oil. And from the pier to the Bosch level, you fill with coke. And then above it, fluxes. You should add fluxes. Apart from that, a small amount of old blast furnace slag is also can be charged with coke after coke level is rise beyond the hot level. And then above it, you have ore, limestone, and coke are charged up to the stock level, to stock line. So in this way, we should fill the entire blast furnace. Okay, starting with firewood up to the clear level, then coke, the Bosch level, then fluxes, then you have ore and coke up to the stock line. So once you have filled, then we should go for lightning. Again, lightning will be done by inserting. You will be having in a rod, a big rod. In front of it, there will be a cotton which is dipped in oil, and then that is lightened up, and that rod will be inserted into the blast furnace through the piers. So you can see in this particular picture. So this is how basically um, rod is inserted at the front. It will be cotton dipped in the oil, and that is fired, and this will be inserted into the blast furnace through the piers, so that the fuel, whatever it is present in front of the 2 years, that will be get ignited, and furnace starts generating the heat. So that is what it is mentioned. After filling, the furnace is lighted by inserting red hot bars through the tuyers or slag hole and iron notch. Because as I told you, these are the inlets through which you can insert something. So generally, high combustible material is kept in front of the tuyers during filling to light up the furnace readily, and burning is allowed with the natural draught for first 24 to 36 hours, and after that a light blast is applied, and as soon as a good amount of gases are emerging from the furnace top, the blast is blown, gradual increase, and until it reaches a normal level in 6 to 7 days. So once a good amount of good amount of gases are emitting out from the top of the furnace, then the dust catcher, damp wall, whatever it is there, because that is actually your uptake and the downcomer. So the valves which are there, so those are will be opened, so that the exit gases can pass through the gas cleaning systems. Uh, so usually more than 3/4 of the standard volume of the blast is blown by the end of the fourth day, and full blast is will be on by the end of the week after the furnace is ignited. Um, so there is an indication that a good amount of heat is generated within the furnace, and that heat is actually melting the slag which we are actually added in the blast furnace. So that you'll come to know when sudden decrease in the outcoming gases through the tap hole is taken. So as a sudden decrease in the outcoming gas through the tap hole is taken as an indication of the beginning of the slag accumulation in the hearth. When sufficient slag accumulates, it can drain it off, and after the hearth is full, the slag and hot metal are drained out, and after the first cast is over, charging and tapping schedules are established and strictly adhered to until routine production is established. So once the required temperatures are attained or generated within the blast furnace, then you should start the charging and tapping schedules for the blast furnace, and to attain proper melting of burden within the blast furnace and the formation of good amount of slag and hot metal, it will take certain time. That is, approximately it will take one week to maintain a proper tap to tap time and all. Yeah. So this is how, as I said, the red hot rods are inserted, and this is the inner view of the blast furnace at the beginning stages. Um, so this is nothing but the blowing in process. So now we'll see some of the technical terms which actually we use during the working of the blast furnace. First one is the banking. Banking, see, usually once you start any blast furnace, that will continuously work for at least 10 years, minimum 10 years. And during this 10 years, it may produce approximately 6 to 10 million tons of pig iron. So that is called as campaign life. Okay, so then for any of the reason, like if it is any damage occurred, or if you want to go for some relining, or some water leakage is happening, in anything, for any of the reason, if you want to temporarily shut down the blast furnace for any repairs, then that is called as banking. So again, if you want to again restart it, again we need to follow the same procedure for whatever the procedure we have followed for the blowing in process. So how to do this banking? You see, um, first we should take off the blast, and then whatever the metal and the slag which is accumulated in the hearth of the blast furnace should be tapped off, and the tears and the notches are sealed with the clay. The dust catcher wall, whatever it is, that should be closed, so that you should isolate the blast furnace from the gas cleaning systems. And furnace will be restarted by doing certain necessary replacements and follow the same procedure, whatever we have to follow for the blowing in process. So a temporary shutdown of the blast furnace, nothing but the banking process. Once you again restart the furnace, after your repairs is done, then again you should follow the same process of blowing. Next one is the fanning. Fanning actually we do if the full production capacity of furnace is not required for any of the reason, and it should be decreased by reducing the blast input. If the blast is reduced to a value less than 25% of the normal volume of the uh, blast furnace blast, then that is nothing but the fanning. This is somewhat better than total shutting of the blast furnace. So whenever you don't require the full production because of any of the reason, then instead of shutting down the blast furnace completely, you can run the blast furnace with the low production capacities just by reducing the blast by 25%. Other one is the backdraft. Um, whenever the furnace is required to be put off the blast for a short duration of time, um, for an hour or two, for to repair any part, or especially the tears or the skips or the cooler part of the blast furnace. So the blast is put off and the muzzle pipe is put under negative pressure, so that whatever the blast which you are sending, that will be taken back. So the so this is called as a backdropping. Yeah. So whatever the blast you have, just now I have shown you that we have a main pipe, a hot blast main pipe, and the muzzle pipe. So whatever the blast you're sending to this, you should take it back. Okay. So that is nothing but the uh, backdropping. Other one is the tapping. Tapping is nothing but uh, removing the liquid products from the blast furnace. Not only blast furnace, from any furnace or any converter, whatever it may be, into the ladles. They're transferring the liquid products from any furnace into the ladle. Uh, it's called as a tapping. So here we basically tap both hot metal as well as slag, and inside the blast furnace also these two will be laid one on each other. As we know, the density of the slag is less compared to that of the hot metal, so the slag float on the surface of the hot metal, So when you tap the liquid product from the blast furnace, so in that scenario also, the hot metal above which the slag is basically floating and coming out from the blast furnace to the runner, and it will be in the runner. There is a provision for the diversion of hot metal as well as slag, so that hot metal will be collected into the torpedo ladles or the transport ladles, and the slag will be collected into the slag pot. So for 1 ton of hot metal is produced nearly around it depends on the kind of practice which we are adopting. So the slag maybe it may range from 500 to 700 kg that is produced for 1 ton of hot metal. We generally tap this hot metal every 4 to 6 hours. Again, this duration is also purely depends upon the kind of the process which you are adopting, and it will vary from plant to plant. Okay, I'll stop it here. In the next class, we will discuss about burden distribution inside of the blast furnace.